Sorry. Okay, welcome back to part 2. So, I have a question for you guys. The buoyant force is greatest in a 10-ton ship if it is floating in fresh water, salt water, which is more dense, and mercury. So, I want you guys to take a moment, copy this down, commit to an answer in your interactive science notebooks, and then we'll come back and discuss it. Welcome back! Okay, so in order to answer this question, let's look at a free body diagram. So, we have the weight of the ship going down, and what's holding the ship up? The buoyant force, of course. Okay, and is this ship gonna just fly out of the water or sink into the water? Well, hopefully not either. So the acceleration is 0. And what is that fancy word that we have for 0 acceleration? Equilibrium. Okay, so if the buoyant force is equal to the weight, did we account for what it was in over here? We didn't. So this was actually a trick question. I promise we won't do this to you on quizzes or tests, but it's fun to do during lecture. Okay, so it's all the same. It's all the same. So if you thought I was tricking you, I was this time. Okay. What does change? Okay, so there is something that's different about the ship in all 3 liquids. Fresh water is the least dense. So in order for it to have, the ship is going to be very deep in the water. And in salt water, just like in a Dead Sea, that picture we had of the Dead Sea, the Dead Sea is more dense, so people and ships tend to float higher. Mercury is so super dense that most of the ship would actually be out of water. It would look very awkward and weird. Okay. So here is another question for you guys, and I promise it's not a trick. We have 2 pieces of wood. One is like a balsa wood and one is oak. So they're both wood, but they're different types of wood. And which block experiences the larger buoyant force? So your answers could be the darker wood, or the lighter wood, or the same buoyant force. So why don't you go ahead, copy this down because we're going to be discussing it, and I want you to commit to an answer, say this is what my answer is, pause the video, and then we'll come back. Welcome back! Okay, so let's see. Now, Archimedes' principle states that the buoyant force is equal to the amount of water displaced. So since this block is displacing more water, or another way to think of it is more of the block is underwater than this block, which is displacing less water, then the buoyant force for this block is bigger than the buoyant force for this block. Since they're floating, the buoyant force is equal to the weight. Remember Newton's second law, F net equals ma. What's acceleration? What is the acceleration of each of these blocks?
0!
Yay! It's 0! Okay, so that means the buoyant force has to equal the weight for each object. So this would be more like balsa wood, very light wood, and this would be more like oak, very heavy wood. Even though they both float, they're both the same size block, this has a greater buoyant force because more of the block is underwater. So, oak, balsa wood. What should you remember? Archimedes' principle always applies. Like F net equals ma is always true, whether an object floats or sinks. The buoyant force is always equal to the weight of the fluid displaced. Now, special case. If an object floats, the buoyant force is also equal to the object's weight. But that is only for floating objects. Okay, so take a moment, pause the video, make sure you have this. This is the key point. And when you unpause it, Ms. Holyfield will be up here to do an example problem with you. Oh, we're gonna get a helper.
Okay, we got Louisa in the house as well. Okay, so we're actually going to jump into a problem that we can solve dealing with buoyancy, so that we can actually just get our hands dirty with how to solve a problem dealing with buoyancy. Here's the problem. There's a cube of wood, 20 centimeters on each side, is placed into a tub of water and is found to sink so that only 6 centimeters of the block is above the water. What is the density of the wood? So, this might seem really overwhelming. How would I even figure that out? So we're gonna take it step by step on the whiteboard, and then again we'll do it one more time on the smartboard, so that we all can understand how we would approach a problem like this. So I'm gonna redraw our block of wood, our cube, and we know that 20 centimeters is the side of the cube. 6 centimeters is actually above water, and I know that buoyancy is going to be dealing with what's underwater, so I actually want to know that 14 centimeters is underwater. That's going to be important to me, I know, at some point. So how do I go about solving this? Well, as Ms. Bauer told us, we know that this cube is actually floating. So I know that the weight of the Earth on the cube is going to be equal to the buoyant force on the cube. So that's going to be our free body diagram, and the acceleration is 0. So in this case, just like you have written in your notes, we know that since the acceleration is 0, we know that the buoyancy is equal to the weight of the object. In this case, it's the cube. Okay, so I know that buoyancy is a measure of the amount, it's the weight of the fluid displaced. So I know that it's going to be density of the liquid, so that's rho, and that's a little L there, times the volume displaced times gravity. Another way to think about this is mass right here, because density times volume is mass. So this is the weight of the fluid, and that's going to equal the weight of the cube. And the weight of the cube, we know that weight equals mass times gravity, right? Well, I don't know the density of the wood, but I know that I can break up mass into, I'm going to draw a little arrow here. We know that mass is density of the cube times the volume of the cube. So I'm just going to rewrite this down here. So this is the density of the liquid times the volume displaced, or under the water, times gravity, is equal to the density of the cube itself, that wood, times the volume of the cube, the whole cube itself, times gravity. So this is actually, this makes it really easy for us to figure out what we want to figure out in the very end, which is the density of the cube. So, do I know the density of the liquid?
Yes.
Do. Yes. We're in water. Do you guys remember what the density of water is?
Yeah.
What is it?
Say 1,000.
Yes, 1,000.
Yay! Good job, Louisa.
1,000. What would the volume displaced be? Well, let's look back up here. I know that this is a cube, so I know that it's going to be 20 by 20. And then displaced means what's underwater. So it's going to be times 14. So my dimensions are 20, this is centimeter, by 20 by 14 centimeters. And then times gravity. And then the density of the cube, we don't know, that's what we're trying to find out. The volume of the entire cube is 20 by 20 by 20. And then times gravity. So this is beautiful because we only have one variable, and now all we have to do is some algebra.
Woohoo!
So why don't
Plug
you
and
get a little
chug.
practice with that? pause the video and just try and figure out, now if we get to this point, can you figure out what the density of the cube is? So pause the video and figure it out. And we're back. So you guys should have gotten 700 kilograms per meter cubed as our density. Yay!
Yay! Woohoo! That looks hard. Can you show me again?
Yes, let's go over it one more time on the smart board. Let's go over here.
Oh, thank you, Miss Holyfield.
Of course. Okay, so first we started out by drawing our free body diagram. And we know that it's floating, so we know that the buoyancy is going to be equal to the weight of the cube. Don't get up. That doesn't mean anything.
Class is not over
Class is not over.
yet.
I know, it's a bell. So the acceleration is 0. We already knew that. So this is just setting our weight equal to, the weight of the Earth on the block is equal to mass times gravity. We talked about that. But we're not really concerned with mass so much as we are with density, because that's what we want to find out. So we're going to change mass into density times volume, and we'll be left with the density of the block times the volume of the block times gravity. So this whole thing is just mass times gravity. Based on Archimedes' principle, when an object is floating, the buoyancy is equal to the weight of the object. So this orange part of the cube represents what's underwater. So that's actually what is going to be the volume when we deal with the buoyancy. So that's the best way to see it, is to just by putting it in a different color. So the buoyancy, so this is if we were to be over here again, this would be this side of the equation. So the weight of the water in the castor box is mass of the water times gravity. Well, we want to change mass into density times volume times gravity. So we're doing a lot of substitution. I know it can seem overwhelming, but just stick with us.
Nah, we got it. We're smart.
Okay, good. So this is where, this up here was dealing with the weight of the box itself, and this is dealing with the buoyancy. And we can actually set these two things equal to each other, because we know that the weight equals the buoyancy. So I just took this here, and I put it here, and I took this, and I put it here. So then we're just, we can take out gravity, and then we can divide by the volume of the box, and we are going to isolate the density of the box, and then we plug everything in that we know. We'll be left with 700 kilograms per meter cubed.
Yay!
So, if this seems really overwhelming, we will be going over many more problems like this, but take a moment to copy this down so that you have it in your notes, and we're going to give you guys some practice problems with both pressure and buoyancy in a moment. So thank you guys for paying attention. We had fun doing this. Miss Bauer is going to come back up here.
Actually, just...
Okay, so each of you guys will get a packet of half sheet of colored paper problems and some instructions here. The instructions, please read them. They explain the homework very thoroughly of what you guys have to do and what we want you to do. So in your interactive science notebook, on these two pages, so for me, again, it was page 18 and 19, you should have the notes from the video that you guys, the two videos, this one and the previous one that you just saw. And for Miss Holyfield, that was pages 20 and 21. So for me, you turn the page to page 20 and 21. And what I want you to do, Miss Holyfield also, on the next page. So for me, it'd be page 21. For Miss Holyfield, it's page 23. We want you to take this packet of problems, undo the paper clip, and then trim the sides of the papers, and then tape the papers as a flip book onto your right side of the page. We want you guys to try these problems for homework. Try your best. If you get stuck on any part, or if you think it's easy, write down notes to yourself in full and complete sentences on the left-hand side. This is your reflection side. So try the problems here. Write down your reflection of each problem on this side. The first couple problems are on pressure, and the last few problems are on buoyancy. So I suspect possibly the first problems will be easy for you, and the last problems may be challenging because you haven't really had practice with buoyancy yet. The key here is to try your best, see where you get stuck, recognize a place that you get stuck, and then either put a post-it note or a note straight on to where your problem is, and then over here try to explain in full complete sentence where exactly you got stuck so you can articulate that to your lab partners and also to me and Ms. Holyfield when we return next class. And we'll be doing a lot of practice problems and hammering out those rough edges and areas that you guys have with solving these problems. So this will help you address where you need help, and it'll help us to figure out where specifically to help you in solving these problems. Okay, so I hope you guys have a wonderful and fantastic day. Please look on Moodle. We are on Cycle 2, Day 3 for your homework and to access these videos in the future. And have a wonderful day.
Bye!